What makes people think and behave differently? Differences in the physical connections of the brain are at the root of what makes people think and behave differently from one another. The neocortex is made up of many smaller microcircuits of brain cells, each consisting of around 10,000 neurons interacting in a space as small as 1 square millimetre. The structure of the neocortex varies across the neocortical mantle to govern the physical size of the principal neurons. Neurons process information differently depending on their location and connection. There is a long-standing theory that the neurons in these microcircuits function and interact in a very standard way, so all microcircuits must operate in largely the same way. Professor Stephen Williams and researcher Lee Fletcher of the Queensland Brain Institute, Australia wanted to know if this is really true. Does a defined class of neuron work the same, no matter where they are located in the cortex? Neocortical topology governs the dendritic integrative capacity of layer 5 pyramidal neurons, published in Neuron on November 21, 2018. Using high-resolution MRI imaging of the brain, they examined the structure of the cortex, and found that the thickness gradually increases up to threefold from the back of the brain to the front. They also discovered gradual changes in thickness can be found even within a single functional area of the brain. When Williams and Fletcher took an even closer look, they discovered that the thickness of the cortex directly relates to the length of individual neurons. A neuron in a thicker area of the cortex is more elongated than a neuron in a thinner area. This, in turn, raises a critical question, says Williams: do they still work the same? To understand this, the team took a step back, and look at how the brain processes information. In addition to processing sensory input, the brain also generates an internal model of the world. Moreover, the brain continuously compares sensory information to its internal model. In fact, such comparisons happen even at the level of individual neurons. For a neuron to be able to compare information coming from two very different sources, the internal model and the senses, it needs two integration zones that interact with each other. One area of the neuron integrates information arriving from the internal model, and another integrates information coming in from the senses. Because they are separate and interact, it's possible for a comparison to be made between the two types of information. Longer neurons from the thicker cortex possessed two integration zones. But this was not the case for the shorter neurons. They work quite differently. Electrically they are even more distinct. The shorter neurons only have one integration zone for processing sensory information and the internal model, so they can't compare the two different types of input. So, one can perform comparative integration, the other can't. Thus, depending on which part of the cortex these neurons are found, thicker areas versus thinner areas, these neurons function very differently. The thickness of the neocortex governs not only the anatomical structure of neurons, but also their electrical properties. The findings revealed the complexity of computational strategies employed in neocortex, and suggests the neocortex is composed of computationally flexible circuits. These findings challenge foundation theories of the operation of the neocortex and set the stage for future research into how networks of these brain circuits operate. The next step is to explore how these differences drive cognition and behavior. After all, given the importance of maintaining and updating our internal model of the world, why do some neurons opt out of this? The small neurons are supersensitive to inputs coming in. That information will spread directly down to action potential output without the need for any further integration, forming a high-speed system. In other words, computationally flexible circuits that enable the brain to make comparisons between an internal model of the world and the senses, yet provide shortcuts when needed, are probably very useful for how we can interact with a complex environment, but can react fast to survive. Thank you.